Appreciate it. Thanks very much. Good morning. Thank you for inviting me today. I'm going to be talking about path planning and sequencing. It's a short period of time to talk about a large topic, so I'll be dancing across lots of aspects of this in the journey towards the interesting questions, which actually come at the end. Trimble is a commercial company, and they have commercial offerings both in the agriculture and civil spaces. If you Google any of these product names, you will find these types of automation products in these different industries. I have the pleasure of being able to work across these industries, and I often compare and contrast agricultural problems with civil construction problems. At the end of the day, it boils down to Trimble products that provide accurate positioning and pose estimation, and marrying that with steering and implement control. And that produces operator guidance and efficiencies and execution in the field. What I do is I extend these baseline capabilities with path planning and sequencing. I focus on optimization and autonomy. This is a research prototype path planner, which is not a product, because I have to declare it's not a product, it's a research prototype. But it takes inputs of mission types, vehicle parameters, the tool and the task, as well as the site characteristics, in order to calculate trajectories for autonomous and semi-autonomous vehicles. There's an illustration from agriculture across the side there. Agriculture is full of obstacles, these fixed obstacles, which tend to be power lines and windmills, as well as ponds and things like that. Here's some additional examples of calculated coverage plans for agriculture. This might be for spraying, seeding, tilling, harvesting. I want to show you the exotic nature of the inputs that you'll see both in terms of vehicle type as well as the domain in which you're trying to execute. On the civil side, you'll often see things like compactors and dozers, and the nature of the coverage plans change slightly, but it's typically only based on the vehicle characteristics and the tendency in construction for us to do reversing turns rather than forward turns. So these are examples of the autonomous compactor prototype doing autonomous compacting over arbitrary work areas with obstacles. There's a fuller problem space here, which I'm assuming most of you are familiar with, where we divide the domain down into strategic, tactical, and controls. We do that within Trimble ourselves as well. Strategic, if you're not aware, is around schedules and allocations. If I have a particular problem and I want to assign assets to that, how do I assign my assets to that task in order to accomplish an objective? Once you have defined what a particular task or objective is, then you can assign a vehicle to that and then calculate the necessary trajectories in order to form that result. And of course, you have a control systems which sits on the actual hardware and will track the vehicle to the waypoint in the line in which you're specifying. I'm going to be focusing here on individual machine plans just because of the length of time we have. The strategic layers are extremely fascinating as well. When you compare agriculture and earthworks, you see a lot of terms and terminology differences between the two, but the concepts generally tend to be the same. For example, in civil, you'll talk about slots and lanes. In agriculture, you'll talk about tracks and rows and swaths, but essentially it's the same thing. There are some concepts in agriculture that aren't as defined in civil, specifically around end row turns and managing headlands. But you'll see in the analysis that ends to come, those properties end coming out anyway. And what I'm going to do is jump through a bunch of these topics at a high level. I'm not going to talk about obstacles. If you want to talk about obstacles, I can talk about that offline. But there's a bit of a pyramid here of complexity. If you start at the particular line transitions, it's where you get your end of row turns. We'll go through row sequencing, block sequencing, and define what that is, and then get to multi-machine coordination. These tend to be spatial in nature. There's also temporal elements in nature, which for brevity, I'll skip today. Line-to-line transitions, what we're really talking about are adaptive turns or end-of-row turns. A lot of the consideration has to do with whether the vehicle is capable of going from one row to another within the steering and dynamic capability of the vehicle itself. The blue lines are a situation where the rows are so narrow that the vehicle needs to make some wide, broad turn in order to attach itself to the next row. And the one in the green is a more lazy one where the vehicle's capabilities can achieve that without any special exception. But you also have additional constraints in terms of attaching to a headland or a boundary, or deciding when or when you do not want to do that based on optimality. We tend to solve these end-of-row turns based on optimal rather than any templated or engineering templated turn. There's very specific reasons we do it optimally. If you're in this space and you're doing engineered turns, I would suggest we chat because there's certain difficulties that arise when you do that, which will find yourself in a sticky situation. On the civil construction side, as alluded to earlier, we have reversible vehicles like dozers and compactors. The end-of-row turn tends to be what we call a shark fin turn, where you're accomplishing that end-of-row turn and reversing the direction of the vehicle. Of course, you have forward turns in civil as well. For example, scrapers do forward turns. They don't do reversing turns. So the superset of end-of-row turns within civil is broader in general than in agriculture. That's the end-of-row turn. When you're going from lane to lane, you want to make choices about sequencing those lanes. Just to set this up, I'll give you a simple toy problem. We're going to take the sprayer and we're going to spray this particular field. In other words, what we're trying to do is cover all the rows with spray. A simple way of doing that is to increment your rows as you go one after the other. We want to do this quickly with minimal waste. And what I want to do is just define what waste means here. We often talk about the vehicle and vehicle dynamics, but it's really about the implement. The implement is the thing that's doing the work. In the case of spraying, we want to spray the field. Specifically, we want to spray the crops on the rows. When we do an end-of-row turn, we're not spraying. So that's actually what we consider transit waste. You also have transit waste entering the field and exiting the field or the work area. So if you look at total length, I'm not sure how to dismiss this little black box, but I'll try and move it out of the way. If you look at total length, it's a summation of your coverage where your implement is actually doing useful work, and the overhead, which is your transit waste. If you're going to also consider end-of-row turns and notice that the end-of-row turn is a source of transit waste, one source, you'll notice that the track direction and the boundary shape will influence the number of end-of-row turns that you have. So if you have an opportunity to optimize the directionality of your rows in your work area, you can actually limit the number of end-of-row turns and find a minimum there. That was one strategy for you to reduce your transit waste. Going back to basic row sequencing, if you're systemizing this, there's a simple algorithm in order to define all the different possible sequences that you could have of rows. Here's a very simple progressive sequence of +1, +1. But what you find, as I alluded to earlier, is some vehicles cannot make the transition from one row to the next due to the geometry of either the end of row or headland or the vehicle itself. You have to do some compromises there. In agriculture, you'll see this as skip rows. So essentially we'll skip a row, but the operator needs to keep an accounting so that he fills in the gaps. One common accounting is something called racetrack, which allows you to skip every other row. It forms a series or a cycle or a set, which can repeat across the field. And that way you'll run this algorithm and you'll cover all of your rows. In agriculture, there are other constraints. For example, the vehicle itself might only turn right rather than left. So how can you sequence your rows in a way which you only turn right? There's a harrow pattern which exhibits this property. And if you sequence your rows in this order, then you will accomplish that result. You might want to ask, why would you only have a vehicle that can turn right? Has often to do with line of sight. If my implement could be blocking my line of sight to my left, so I prefer turning to the right. In construction, you often see simple progression of row ordering. Instead, what you'll see is that we dwell in a lane more than once. So we'll compact a lane more than once, we'll push in a slot more than once. So this falls under row sequencing, except that you're repeating rows. And again, you can come up with algorithms that define these. Okay, so that was end-of-row turns for line to line sequencing. Now we're going to go into blocks. What is a block? Well, I'm just going to, again, pick a toy problem. Say you have either a set of work areas or a farm, and that's your home base. What I want to do is I want to visit each of those work areas, do the work, and I want to minimize my transit waste from block to block. If you look at this as a little toy problem, you'll notice something curious, and that is if I have an odd number of rows and I enter in the lower left, I'll exit in the upper right. If I have an even number of rows and I enter in the lower left, I'll exit in adjacent lower right. All the combinations and permutations of any evens and odds essentially reduce this down to sets of blocks that have 4 ports. Whatever port you enter and the characteristic of the orientation of the entry and exit, as well as whether it's even or odd, will define your exit point. You can use this to your advantage in order to traverse all of these fields and minimize the transit waste between the two. If you abut the exits with the entries, then you will minimize your transit waste, if you're so lucky. If you're not, you'll add extra transit waste. And we'll talk about that point again at the end. But in reality, farms and job sites are not rectangular blocks. They look like this. So does this still apply? Well, let's go ahead and grab a field. This happens out of Eastern Europe. And we're going to try and do the same sort of progression across the field. We're going to spray this crop. I'm going to just arbitrarily choose sweeping from the left to the right. And we'll just go ahead and see what happens. If you do this, you'll notice you'll skip those 2 rows. Well, that's okay. At the end of my sweep, I can return and pick up those 2 rows, or within the sweep, I could interrupt it, pick up the rows, and resume. Now, if I were to minimize this, I want to minimize that transit waste. So I want to pick the one that's actually the shortest detour. What are we really talking about here? Blocks emerge from shapes that are concave. So complex concave shapes will naturally exhibit blocks and block behavior, and you'll have to solve the block-to-block problem, and that's the source of transit waste. So there are simply 3 blocks in this. They all happen to be even. That was just by chance. So I've got 4 orientations for each one. This leads to 384 possible transits across this field for these 3 blocks. I'm going to go ahead and brute force this. 384 solutions, solve them all, resort them by shortest to longest. And I find for this toy problem that there's a 900-meter spread in 10 kilometers, or about a 10% change. So it matters how I'm going to order my blocks. An interesting question to ask yourself is the operator doing the optimal one? Well, he's got 1 chance in 384 of doing it. He's an intelligent person. He's probably doing pretty good. The other thing to notice is that the spraying of the work of the implement is constant regardless of sequence. And that's because you're going to spray every row. Once you've done that, you complete. Every row is visited regardless of the order in which you do it. What's varying is your transit waste, both end-of-row transit waste and block-to-block transits. So how did we do? Well, my naive way of spraying this field is actually 500 meters longer than the optimal. So if you followed my guidance, then you would have spent 5% more time and fuel every time you visited this field for both spraying or whatever activity you were doing. Analyzing the operator, he was actually 300 meters longer than the optimal. Now, like I said, every work area is a snowflake. They're all unique. Let's take a look at another one. Here's another field in the same region. If you break this down into sets of convex shapes from the complex concave shape in order to identify your blocks, you'll find that there are 13 blocks in this field. The number of combinations and permutations of transits for 13 blocks exceeds 417 quadrillion. So I ask yourself the question again. The operator that's spraying or seeding this field, or the operator that's maybe spreading material in this geometry, are they doing the optimal or the shortest? Likelihood they are not. There's always room for improvement. Now, the question is, how are you going to calculate that one? Well, today we bring out the quantum computer and give it a go. It's designed for these types of problems, and we get a result. So here's our quantum solution for that 13-block problem. We don't have to wait lifetimes or the age of the universe in order to figure out what it was. But the question you should be asking yourself is, there's two of them, is this the minimal solution? And the technique we used, could it find the minimal solution? There's actually an answer, a fairly straightforward answer to validate this. And if you're interested in this particular area, feel free to reach out to me and we can talk about it further. But what I've given you is 1 in 400 quadrillion. So you could believe me or you could try and check me. But there's a way that you can validate this in a trivial way. The safest claim that you can make is something that Google Maps will do to you every once in a while. It will say, hey, I found a better route. Well, that's what we can do too. We can say, hey, we're going to drop the claim of optimality. We're not going to say this is the shortest route. We're just going to say, compared to your normal behavior, this one is better. And we can actually tell you how much better it is because we have both solutions. So that's our current position. Move on to multi-machine coordination now. We're going to quick time check. 10 minutes. Okay, cool. Multi-machine coordination. So we've done end of returns, row sequencing, block sequencing. Now we're going to apply the vehicles to these spaces. And you find yourself with two different problems, one loosely coupled and one tightly coupled. For construction vehicles, you can execute excavators, dozers, scrapers, compactors, and trucks loosely coupled. What that really means is each member of the work group pulls from a common pool. It does its activities independently. And then by doing that, you can do your work in parallel. Here is an example of 3 compactors compacting a common area. And the way they accomplish this is they're drawing up from the pool of rows as work to be done as they become available. So it's a simple queuing problem and a distribution problem across the group of vehicles. Each vehicle is working independently, as long as they don't intersect and collide, and they can parallelize the task. You can do this a lot in civil, heavy civil, when you bring in more than one vehicle in the same space. In agriculture, you won't necessarily see as much of this type of loosely coupled work group. Instead, you'll see more tightly coupled work groups. Tightly coupled work groups show up in civil in the mass haul problem, where you are excavating, loading, carrying, dumping, spreading, and compacting. Each member of the work group, if it participates in a material handoff, is a big clue that you are now have a tightly coupled coordination problem. That serializes the work, and the effectiveness is now around the material flow through the system, not just the transit waste which comes out of coverage. A dozer can do all of these activities individually, and if you're in that situation, then you can use them in parallel and you're loosely coupled. However, whenever you move the mass from one vehicle type to another, that's when you get tightly coupled behavior. Excavator dozer pairings, loader dozer truck, excavator truck and dozer. These are specific challenges that are in the industry right now. If you're looking for a space to play in, this is a great space. All the other ones, in terms of parallel loosely coupled, are well solved. Now, in closing, what I want to do is talk a little bit more higher about determinism and comparing agriculture and construction. So if you're in this area of research, you'll find that the parameter space and the state space and the decision space is very large. It's significantly large enough that in order for you to be commercially successful, you have to solve a significant amount of it before you can provide it a compelling option. That's what makes it interesting. It's probably why most of us are here. On the green side, there's ag. On ag, we're concerned with complete coverage over a regular lattice. That set of rows tends to be well ordered, and we call it a lattice, and we end up traversing over that lattice in the most efficient way. In contrast, in civil, we're concerned with excavation of volumes over a sparse, semi-irregular lattice. In other words, our work area exceeds the size of our sub-work and activity, and we're free to work any way we like within that zone. We're not necessarily constrained to a particular lattice. The decision space in agriculture is discrete. I showed you a little bit at that in the examples. The decision space in civil is continuous. Well, it's continuous today, although I posit that we need to shift that into a discrete space. The advantage in ag is the decision space is also reused and reusable. spray pattern I have for a particular field will work on Monday and will also work on Friday. However, in civil, the decision space is volatile. As soon as I apply the mass Hall to a portion of the problem, the environment has changed and I have to recalculate. There is no reuse of the decision results from the previous activity. That makes it somewhat unique. Research areas in agriculture. If you're looking to minimize transit waste, what you want to do is actually manipulate the coverage strategy to minimize the transit waste. What does that really mean? It means that if you have an odd number of rows in your field, make it even, if that's to your advantage, and give up the extra row. Now, you might argue, well, that's a productivity issue. I'm going to give up a crop or an amount of yield. And the answer is, yes, that is true. But if your cost is more than your benefit, then you must give up that row. Now, you argue that a farmer will never do that. But if you look at the telemetry, you look at the telematics, they do it all the time. A spray operator who's a subcontractor will spray a field. He will see that it's a waste of his time to go in that last row and he'll skip it and he'll go home. They're already doing it. They just don't admit to it. On the civil side, what you want to do is reduce the desire for an operator to intervene. That's where you get continuous decision space. If you can reduce that, and we're seeing that in autonomous compaction as well as excavation. We protect against undercut and we allow the operator to execute his task, although we guide the bucket to grade. That reduces decision space. He trusts it, and between that moment of stroke, he's not in control. We need to increase the number of moments that are not in control and reduce their decision space. This will enable discrete decision-making and bring the problem into control. And there are techniques to do this, which we can talk about further as well. Okay, so that's a rapid tour through path planning and sequencing and how it affects ag and construction.
Right, thank you very much for your talk. We'll open up for a round of questions from the audience. If anyone has a question, you're welcome to step up to the mic over here, ask a question. Maybe I'll start with one question. So in civil and in agriculture, there's obviously a lot of variability in the field conditions and the job sites, and maybe some assumptions or plans that we make for one field, we'll find out those heuristics or assumptions maybe don't carry over to the next side or next field. So what do you think is the best approach to handle those challenges?
Yes, so we talk about those in terms of replanning events. When you talk to an operator, they'll always say it depends. It depends on the weather, soil conditions, how I'm feeling that day. All of that is great. But at the end of the day, what it really boils down to is replanning events. There's no surprise here. Any plan that you take into the field will have to be replanned once you experience those unique conditions. So built into the system has to be a replanning event. If you look at the control system, the replanning events on the order of milliseconds and seconds. If that can't handle the replanning event, it needs to be escalated to the tactical level. The timescale on tactical level are minutes to hours. So you have a replanning opportunity from the seconds to convert that into a new plan around cycles, minutes to hours. If you're longer than that, you need to escalate that to the strategic level. And the replanning life cycle there tends to be days or weeks. So you're essentially saying, am I aborting? Can I handle it in the next higher layer? If I can replan around that, I will do that. Otherwise, I'll kick it up to the higher level. That's a really tricky problem to get right. But it's really the only way out of this kind of wet paper bag that you find yourself in. Don't make the mistake of trying to do strategic planning in your control system. Okay.
So how do you intend to deploy this and how easy it is to parameterize the algorithm for my particular problem? Imagine I'm a farmer, I have a machine that is many parameters.
Sure. Yep.
Value.
Yes. So this is a success criteria. So the question is, how do you take the system and define it for a new use case? And how many parameters do you need to tweak in order to make that occur? And in the commercial space, you're dealing with users that do not want to know the parameters. They just want it to work. They're either going to agree with the solution or they disagree with the solution. And they want a big knob that just says better, looser, tighter, faster, that kind of thing. So there's quite a interesting UI UX problem, both on the application of algorithms to new use cases, as well as the user's opportunity to apply these to their particular use case. In agriculture, where you tend to break it down into activities, and there's already activity there, and instead of plans, you talk about prescriptions. So my prescription is to spray. When I define my spraying prescription, I'm defining a strategy as well as a vehicle type. That's where you start assembling. And what you need to hide is the complexity where you systematize that vehicle description in terms of slew rates, in terms of maximum steering angles, in terms of steering geometries, and all of that stuff. You need to hide that away from the user. But as a systems deliverable, you have to be able to have that mapping. So we end up with machine models, and we actually have activity types. You marry those two together, and you will end up with most of your parameter set. The one that will really catch you out is regional differences. So you might be able to solve that completely, but when you find that you go to Germany, oh, they spray their headlands in clockwise orders. Why do they do that? We just do. Or we farm our headlands in Europe, but we don't in Australia. So it's not an easy problem, but you must solve that problem in order to make something commercially viable and within the appetite of the end user. It takes work. But I'm confident that the subsystems are flexible enough to be applied to n number of use cases.
Thank you.
Thanks.